you, Sanjib, for the invitation. Should we test? Should we? Yeah. So thanks, Sanjib, for the invitation. I come from Institute of Physics, which is sort of the eastern coast of India for people who are not from India. This is the information, and there is a picture of our institute. So today I'm going to talk about, briefly have the plan to talk about two parts. One part is inertial, and second part is orientational relaxation and their impact on active particles properties. So this the group to whom I am thankful for all the work, older version and newer version of the group. And today the work I'll be going to present, first part is mainly done by Manish, and many body simulation which was done by Shubhendu, who was a postdoc. And the second part is done by Rajneesh, who is a current postdoc, and a couple of PhD students, Shubhranshu and Raj. And a part of the work was also done in collaboration with Fernando, and I'm thankful to these two organizations for funding and for other kinds of support. Okay, so I'm just giving a little background, assuming that if some people don't know it, but it might be too simple. So what is active matter? Of course, the systems are non-equilibrium, and these systems are such that the energy pumped and dissipated in these systems at the smallest scale, unlike in passive matter driven out of equilibrium by external drive. So these are internally driven, so each individual is internally driven, that we understand. And for biological systems, it's easy to understand. I myself can call myself as an active particle because I can move without external forces. They produce self-propulsion or can produce stress to their surroundings. So this is the brief definition of active matter. And active matter, we know, come across different scales. So starting from molecular motors to intermediate scales like cells. Cells come together to make tissues, or maybe multiple cells swimming together. Intracellular stuffs like actomers, like the cytoskeletal filaments driven by molecular motors, and of course like large scale flux, etc. So with this, I'll just move to the next section. So most of the active matter studies that we do, we assume active matter to be overdamped because most of the situation in which we are interested in, they are really overdamped. So for example, like active colloids. So in active colloids, so one possible example of how active colloids become active could be like a Janus colloid, two different parts of the colloid. This example is a chemical example in which I can imagine that I have an active colloid in one part of which has just a little bit of platinum, and if I put it inside hydrogen peroxide, that platinum will hydrolyze this thing and will generate water and oxygen bubbles. And if oxygen bubbles comes out from this side, it will kick the particle in a specific direction, but this direction is not. So how active matter is different from passive matter driven from outside is that this drive each individual is getting on its own scale depending on its orientation. So whichever orientation this platinum is, this will go in the other direction. So each particle can have its individual different orientations. So kicks will be in individual directions, and this kick will also get. There is a stochasticity by which these chemical reactions happen. So as a result, the kick will have a direction, but slightly there could be stochastic variance in the direction. So the particles will start to move in a persistent manner. So we can think about the persistent motion, and that persistent motion will have a typical persistence time. And this persistence time, for example, in active colloids turns out to be order of a second, whereas given their little mass, their inertial relaxation time is typically 1, 2, or many orders of magnitude smaller than the persistence time. So the two quantities to compare is the persistence time with respect to that what is the inertial time. Since the inertial time is too low, we don't care about inertia for this kind of systems. So these are more examples of active colloids. Yeah, I'm just showing this to convince that they can come together, generate interesting phases. So interactions could be that there could be a simple volume exclusion, or if they move in a certain direction, they can also generate like orientational alignment in propulsion, and that will generate clustering phenomenon. So some clustering could be motility-induced phase separation, some could be flocking. So this happens in the overdamped situation. But there are, of course, like active granular matter, for example, where the systems are much, much bigger. And so this movie is, which I took a video from Nitin's lab in IIT Bombay. So what are these? These are metal rods which are shaped like this, pettered metal rods, which are vibrated on this vibrator. And because of this difference in friction in the forward and backward direction, these guys start to move if you vibrate in the z direction. So the forces are in a direction in which the particle is not moving. Particle is moving in a perpendicular direction to the forces you impart on them. And then you see that they perform persistent motion. And these guys, for example, they are elongated. So if they collide, they will try to align with each other. So there will be also alignment interaction between them. But interesting point to note is that in these kind of systems, the persistence time becomes equivalent to the inertial relaxation time. So this is one example. Other example could be this. So I mean, you necessarily don't need to have a particle which is elongated. You may also design a spherically symmetric particle in which you can give it two different legs, one big, another small, so that if you vibrate, so one part will give rise to larger friction, other part gives rise to smaller friction. So when they jump and fall, if it falls with the smaller, narrow leg, the smaller friction, it will slide more. And if it falls with the larger leg, it will fall and will not move much. So as a result, it gets a directionality, and that's this directionality. It will start to move, but when they collide against each other, those collisions will be spherically symmetric. So one can design those kind of things. And this is an example of Hexbach, which, yeah, so I'll not. But in all these systems, the inertial timescales and the persistence times are equivalent to each other, and inertia can matter. So that I'll try to show. Persistent motion, so this is a cartoon of the persistent motion. So I think all of us understand what it is. So I'll jump to the next slide. So what I showed is that this persistent motion can be modeled by some active Brownian model. And then there can be interaction. Interactions could be repulsion or could be alignment. So these two kinds of interaction. So let's have a closer look at this, what comes out from these interactions. So if one takes active Brownian particles and just put exclusion interaction between them so they don't attract each other. So this was sort of a surprising, interesting behavior at that time when it was discovered around 2012 and 13. And what happens is that if you have these active persistent movers with self-avoidance, with exclusion interaction between them, so they will come if the active self-propulsion speed is high enough and if the density is high enough, so they can come together and make local clusters. So these local clusters, so it will generate like high density and low density region, coexistence of these two, in absence of any attractive interaction. So this was surprising because surprising not in non-equilibrium, but if one thinks from the equilibrium perspective, in equilibrium, we know that the gas-liquid phase coexistence can come about only in the presence of attractive interactions. Without attraction, you cannot have this phase coexistence of gas-like and liquid-like phases. So that can come about here because of the activity, number one, and then there is a, so what happens, how it, the crowding happens is that if two particles will collide against each other with a higher probability if they are self-propelling towards each other. So the probability will be high of their collision. And if they collide, immediately after collision, the self-propulsion direction is not going to turn away from each other. So up to the persistence time, they will try to keep on pushing against each other. So that will give rise to a time scale over which if other particles also join this collision event, they come together. So means that this if things happen, tells you that you will require a certain self-propulsion speed for a given persistence and a certain density. So then there will be this positive feedback that these guys will come together, and then after, by the time it changes the direction of motion from away from the collision. If by that time they are already crowded, they are trapped by other particles surrounding them, there is no way that they can come out of this collision. So they will get trapped. And this trapping makes these high density regions in these systems. So this was in the overdamped system. This nice motility induced phase separation happened. But then later on it was figured out that if you put in inertia in this system, and even if the inertial time scale is relatively small with respect to the persistence time, so this I'm showing this phase diagram. In this phase diagram, this capital M is the ratio of the inertial time by persistence time. So you see that even if the inertial time scale is by persistence time is greater than 7%, 0.07. So inertial time scale is just more than 7% of the persistence time, you lose this motility induced phase separation. So there is no motility induced phase separation anymore. So what happens is that if you have inertia, these guys collide, of course, but at overdamped systems, they were remaining at collision. If you put in inertia after collision, they will jump back, and after jumping back, there is a probability that they will again come to this collision, or if the persistence is not high enough, they may avoid the collision next time. So they collide, but it's not necessary that they will remain in that collision for a long time. So that's what happens qualitatively. And quantitatively, we know that initially I said that if persistence time, inertial time scale is of the order of persistence time, then of course we cannot ignore inertia. But this example shows you that even if the inertial time scale is one order of magnitude smaller than persistence time, even then you lose that phase separation. And this phase separation was a steady state behavior. So means that inertial impact is not only a transient behavior, it leaves a imprint of it at the steady state properties of the system. So you cannot just forget inertia. That we typically do in all our equilibrium-like calculation or dynamics in equilibrium systems, that we assume that inertia doesn't matter beyond inertial time scale, and we can ignore inertia and go ahead writing our equations in the overdamped limit. And of course, we know that our phase transitions, etc., in equilibrium doesn't depend on inertia. So this is something I hope that I could convince that inertia can matter at late time or steady state properties. So that's what I'm going to show what we did on that. So the second part is activity and alignment. Active particles can align. For example, bird flocking was explained using Vicek-like models, in which you say that there is this persistent direction, but this direction is not independent for each particle. A particle can take the direction of the surroundings average orientation, and it takes, if you do that, then they will, so that generates a coupling in the orientation, and that coupling in the orientation generates a coupling in the velocity. And this velocity field, of course, then plays velocity field, of course, then take the local density field with it that generates the current. So as a result, this coupling between velocity and density, what happens is that you have this alignment in velocity, and which gives rise to this flocking, or in the density field, it gives rise to this phase coexistence of high density regions which are moving together and low density regions which might be randomly moving in different directions. So, but in original VCheck model and many other VCheck style models, what people typically assume is that this taking the orientation of the neighborhood happens instantaneously. So I just calculate what is the average orientation of the neighborhood. I take that orientation. So this is the rule by which that update happens. And then there can be some noise. So depending on the value of the noise, I may be able to completely align with my neighborhood, or I can fail. And that gave rise to a phase transition between isotropic phase, isotropic and sort of non-motile phase, and polar phase, in which you have this polar flux which goes in a certain direction. And this model was developed in 1995, and phase diagrams, etc. So immediately Tornat-2's field theory came about, and then these phase diagrams, etc. started to come from 2015 onwards. So took a couple of decades. So around this, there are also these other kinds of model which one calls like flying XY model. So you can imagine that the orientation of these particles are not happening instantaneously like in VCheck model, rather like in XY model in our typical physics systems. So where one can look at the neighborhood and get coupled with that with some interaction strength J, so which is denoted here by gamma, and that will give rise to a time scale. Gamma inverse is the time scale of this orientational alignment. So that gives rise to this time scale of orientation. So we'd like to have a look at, after we introduce that, what happens. So this is the plan. So I have 15, yeah, roughly 30 minutes. Okay, so the plan is that first I will tell you about what we did with the, looking at the impact of inertial relaxation on asymptotic and steady state properties of active particles. And in the second part, I'll look at this orientational relaxation. Okay, so I already mentioned that Y inertia in macroscopic active elements, inertial time, if they become of the order of persistence time, then it not only has a transient effect, it has a late time and steady state effect. So before going into our calculation, single particle level experimental result. So this was, so again, like a vibrobot, which can move in a certain direction. One can look at this guy's velocity distribution, and you see this very interesting non-equilibrium kind of velocity distribution of this guy, and the peaks show that this is the active speed. And then, of course, there is a symmetry in all this direction. And if you look at one projection, this will look like a bimodal distribution around 0. So the peak size is, this separation is the speed of these guys. So that's one thing that happens. And the other thing they measured is a delay function, which is a delay of the, so if you think about an overdamped active particle system, then the active orientation in which the self-propulsion happens and actual displacement of the particle both happens exactly in the same direction. But for this inertial system, there is an inertial time lag. So as a result, what can happen is that the activity may act in this direction, but the particle may move in a slightly different direction. So what is these two directions? This V and U hat is the heading direction. So you can do a cross correlation function of the two, and then design this guy so that if you have time reversal symmetry, of course, by design, this guy will be 0. And this will show you the departure and breaking of time reversal symmetry over whatever time scales. So this was the quantity which was measured, and which showed that, of course, at the beginning, Vt is equal to 0, this is 0, and at very long time, they get completely these things become, the correlation dies out. So as a result, again, it goes back to 0. Okay, so before I get into the details of the calculation,
So you are saying that inertia is making the process sort of Markovan. So
which one?
Inertia, because you are
Inertia, yeah. So it's sort of, I mean, a little level, right? Because that has memory, that inertial memory. So it's kind of a like Ornstein-Uhlenbeck kind of a process that we know, but that process along with activity, so these two together keeps the information for the late time behavior. So what happens is that again, whatever expressions we will derive in that, if you set activity equal to 0, of course inertial impacts will all cancel out. Okay, so before I get into the details of the calculation, so these are the take-home messages, I think, from the work that we have done. So unlike in equilibrium, inertia affects late time and steady state properties. Number two is that okay, so in this work, I'll show you that we determine the inertia dependence of kinetic temperature, swim pressure, entry production, diffusivity, mobility, whatever people typically measure. We'll show you some exact analytical calculations for free and trapped active Brownian particles. Free and trapped active Brownian particles, but inertial in the presence of inertia. And for interacting active Brownian particles, we'll show you some numerical simulations and give you some approximate expressions, which are sort of like we use our experience from the analytic calculations wherever we can do it, and to write down these expressions. And then there is a generic statement that what we find is that inertia restores equilibrium-like feature. It sort of kills the non-equilibrium features of activity as you increase inertia. Okay, so this is how we model it. So you can think about a free active Brownian particle, an active Brownian particle in trap. And how do you do that? Of course, like overdamped, you just write down the equation for theta. Underdamped, you write down the equation for orientation and the angular velocity. Similarly, for position, you write down the position, this dependence on velocity, and the equation for velocity. So this has activity is this guy, gamma v0 u hat, and that u hat depends on theta, this angle in 2D. So that evolves like that. So that's this activity in the dynamics, but otherwise simple thing. So we use these characteristic time scales, the persistence time and the characteristic length scale, which can come from the translational diffusivity and rotational diffusivity. Rotational diffusivity basically gives you the persistence time, inverse of that. So this is the generic set of equations you can write down. So in which this guy I'm just writing down, I can have an external harmonic trap, and for harmonic trap I can perform analytic calculations. So that can be included, and then this is the orientational dynamics. So for the sake of simplicity, what we are doing in the rest of these calculations is that I'll just write the orientational dynamics to be still overdamped, but the translational dynamics is underdamped dynamics. So having a look at what happens due to just translational inertia. Okay, so if I write down this kind of equations, at least in the overdamped limit, so one can show directly that the dynamics of this persistent random walker is equivalent to trajectory. I mean, not the dynamics, the trajectory generated by a persistent random walker is equivalent to a configuration of a semi-flexible filament. So this was a work we did along with Abhishek Dhar, and then the idea there was that we write down these equations, show this mapping, and then utilize the mathematics which was developed in 1950s to understand the behavior of semi-flexible polymers. We can take that mathematics and use directly that framework to calculate stuffs for the active Brownian particles. So that's the idea. And that idea, then we have just extended this in the presence of inertia, what happens. So this is just straightforward extension of that idea. So let me get into that. So you can write down these equations. So the orientational dynamics you can write down either in Stratonovich sense or in Ito sense. But finally, the corresponding Fokker-Planck equation turns out to be the same equation. And this equation, so what we do is that we are not trying to solve the equation for the probability distribution, but
Usually the Fokker-Planck equation is different for it. Right?
yeah, but here you see that Stratonovich equation and Ito equation is different. So the Fokker-Planck is the same equation. Yeah. So I mean, this is the orientational dynamics. You write this down in this either in Stratonovich sense or in the Ito sense, and then derive the corresponding Fokker-Planck. So in the Fokker-Planck, so what we'll do is that we are trying to utilize this Fokker-Planck equation to calculate all the dynamical moments. So that's our goal. So you write down this equation. The terms, specific terms are like this is the velocity term, and this term contains the activity and the dissipation, the drag term, activity and drag. And this is because of the presence of inertia, this is the grad square terms in velocity space, so diffusion-like term in the velocity space, and this is the diffusion-like term in the orientational space. Right? So then one takes this and performs a Laplace transform of these equations, and then what one can do is that so the framework is exactly the same. So first I'll show you the yes. The framework is the same. So you'll just add the harmonic term there. So first I'll show you the results for free particle, and then I'll show you the results for the harmonic trap. Okay. So you write down the any observable you take, write down the average of that guy, and then plug this form in to the previous equation. Then you get kind of a master equation for the for this observable in the Laplace space, and then one can solve this term by term. So one can try to have a look at how one goes about it. Let's say I just look at the first couple of moments of velocity. So v squared and the velocities component along the orientation vector. So if I take these two guys, so I had this generic psi, so I can plug them in there, and then these two equations I can solve simultaneously. So you'll get an expression for v parallel and v squared, so both in the Laplace space. But just if you notice here that all these terms that comes about here has a form like 1 by s plus some si, some constants which depends on the parameters of the system. So as a result, clearly the inverse transform will have exponentials, and all those exponentials, so these guys will come as e to the power minus sit kind of terms. So that you will get in the real space. So one can perform the inverse transform and get, of course, like the time dependence of these quantities as well. And of course, the steady state is much more easier to get. You can multiply this psi s with s and take the limit s tends to 0. That will give you the steady state results. So basically, you can get the whole time evolution, see various crossovers, try to understand all the crossovers, crossover points. Everything can be done analytically. So we'll do this for free inertial ABP. We can look at the velocity moments, displacement moments, etc. The time evolution will take a lot of time for me to explain. So I'll sort of briefly show you that time evolution you can calculate, of course. But we'll focus on the steady state properties. That's the late time behavior, or like for the free particle, the late time diffusivities, etc. So if you look at this quantity, for example, this quantity I showed that in this previous example, the Scholz et al. Example, this was measured from the experiment. So this was the delay function, right? And the delay function here you can calculate, and you can show that this delay function, of course, at very late time will go to 0, and t tends to 0. This also goes to 0. These two terms cancel. Intermediate times, they show departure. similar kind of departure like here. Of course, the departure becomes stronger and stronger as you look at larger and larger mass ratio. This capital M, remember that this is a ratio of the inertial time scale and the persistence time. So qualitatively the same behavior. So one can also calculate all these steady state quantities. I'll not. Yeah, so you can one can do all those things. So what we do first is that we showed from the at least the experiment we have seen that this velocity distribution had this bimodal structure, the non-equilibrium distribution, and this velocity distribution is clearly non-Gaussian. So what is the non-Gaussianity? So that I can directly, at least from the moments, I can calculate the fourth moment and calculate the excess kurtosis, and this is the expression of the excess kurtosis that you can calculate. And that expression, one can then check how does it vary as a function of inertia and as a function of activity in this system. So if you look at this quantity, this is just the contour plot of this same this quantity. So what you see is that this is the heat map. So in this heat map, you see that this kurtosis, excess kurtosis shows a strong departure in this region where this becomes negative. This excess kurtosis is negative, and this negativity is basically associated with this bimodality of this distribution. So this part, the negative kurtosis, is due to a probability distribution which looks like that in 2D of the velocity distribution. And at very small value of inertia and large value of inertia, you see that this goes back to Gaussian kind of behavior. This yellow part is close to 0. So one can try to I mean, of course, one can see this from the expression, but also try to understand how to explain this behavior. So what happens at large M? So if I look at very large M values, so what happens is that over the inertial time scale, persistence, the memory of persistence is lost. So there is inertial recoil time scales over which if the inertial persistence memory is lost, of course the system will then look like an equilibrium system because it's sort of, you can ignore persistence then. So that's what happens here. So this part is basically equilibrium-like. What happens there is that even we have a translational diffusivity, so that translational diffusivity, even if I trap it strongly, no, so this is not trap. So if that, even if I look at very small values of M, what happens is that this translational diffusivity will give rise to a fluctuation of the velocity. That fluctuation of the velocity goes as 1 by M. This is like equilibrium picture, right? Translational diffusivity. So it goes down as 1 by M. So as I go to very small values of M, of course, this will then become very high. And I have this bimodality, and the bimodality is coming because of the Peclet number. So Peclet is giving me a length velocity scale over which this distribution will try to maintain a ring-like structure. So basically what happens here is that this, imagine that that ring-like structure is still there. On top of that, this velocity fluctuation is much bigger than this ring-like structure. So that overwhelms this ring-like structure, and that's why it becomes again Gaussian-like at small enough values of inertia. So in between there is a region over which this shows this non-equilibrium behavior. Okay, so this is for the departure from Gaussianity. Using those calculations, one can look at the steady state, I mean, second moment level steady state quantities, which we have some understanding of starting from our equilibrium understanding of the system. So I can look at the kinetic temperature of this. So in this dimensionless form, this one is coming from the translational diffusion. The rest of the part is from activity. You see that this active part, this initially increases with inertia linearly, then to saturate. So that's the kinetic temperature dependence. And saturate to this value at large enough inertia, which looks like the, even for, which looks like, and completely independent of inertia term. the second term is the asymptotic diffusivity. You see that asymptotic diffusivity is completely independent of inertia for a free particle. So that picture changes the moment I put in interaction between particles. So interaction between particles give rise to a route by which the diffusivity also becomes inertia dependent. The swim pressure, one can calculate that also then turns out to go down as a function of inertia. So I was telling that large enough inertia systems will start to behave like mode in equilibrium. So this is one signature, that m goes to infinity, this will be 0. So there is no swim pressure. Swim pressure is due to activity. So activity will not be able to do that. So entropy production rate, if you calculate, that also reduces as 1 by m at large enough m. And if you look for the violation from of the equilibrium fluctuation dissipation relation, so departure of this, so that departure function then one can show is that that's proportional to the swim pressure, and of course that's proportional to the entropy production in the system. And this aligns nicely with Hardas-Asser relation, but we have this exact expression with the okay, so I should remind you that these D factors are for dimensionality. The first D stands for the dimensionality of the embedding space, and D minus 1 is for the orientational dimensionality. Yeah. So this quantity, again, like at very large values of inertia, this will go towards 0. So as if the departure from equilibrium becomes vanishing. So this work was done by Manish. So second part is the trapped active Brownian particle. Again, exactly the same formalism. I just have included this harmonic trap, and then go ahead. One can do the look at the time dependence. So first thing is that in the velocity space, now we have, instead of just 0 and negative values of kurtosis, now we have these 3 different regimes. One regime in which there is still a bimodal distribution with negative values of kurtosis, so this kind of bimodal distribution. Another region in which you have a positive value of kurtosis with the distribution function having heavy tails, and rest of the parts are Gaussian, and this is a 3-dimensional plot in which we are showing this behavior as a function of Peclet number, the inertia on this axis, and the trap strength on that axis. Okay, so and if you look at the distribution in the position space, particle, it's trapped particle now. So distribution in the position space, there you have again just 2 regimes. One is Gaussian-like, another is bimodal distribution with negative kurtosis. So that's this region. So these planes that we have plotted, it's from the expression for the excess kurtosis, and these are also those expressions for the excess kurtosis, and these distributions we have calculated directly from numerical simulation. We did not try to, I mean, in some limiting cases, we can get expression for this distribution, but I'll not get into that details. And this was some comparison with various experiments that are done, either in fibroblots, hexbugs, granular systems, and looking at what are the ranges of these inertial timescale ratios, which goes from pretty much overdamped to very large values, and activity and the trap strengths. So this range is something whatever we have already covered in that phase diagram. Okay, so now here if I again look at the rate of entropy production, rate of entropy production again goes down as 1 by inertia, but it also has a time scale coming from the trapping strength. 15 minutes? 5 minutes. And if you look at the kinetic temperature, similar behavior, and you can look at the steady state mean square displacement. And if you interpret that mean square displacement in terms of effective diffusivity, you see that this structure then start to depend on inertia. And this dependence, of course, this is like, I mean, we are implying diffusivity with this system is of course not diffusive. This is like a trapped system. But then we went ahead to do numerical simulations with particles which are interacting locally by harmonic interaction, but saw harmonic interaction with a finite cutoff, and then tried to test if this expression works. And it looks like that they are pretty much, I mean, at least qualitatively that works, in the sense that dependence of inertia, the scaling behavior is equivalent. Okay, so this part was also done by Manish, and then I can show you quickly what happens in the active Brownian fluid. So in the active Brownian fluid, I mean, if you go to very low densities, you can now again ask for these quantities like the late time diffusivity and all other kinds of quantities. So I'll just quickly focus on the diffusivity as a function of activity. So if you look at this quantity, you see that we have calculated this at different values of inertia. And if I look at extremely small values of inertia, I get the Peclet square dependence that we typically get for overdamped active Brownian system. But as I increase inertia, I see that this power law, and over several decades, but I don't know whether it will remain a single power law all through, this power law, the exponents go down as I increase inertia. Not only that, the value of the diffusivity also goes down. So now we have we already have derived a effective expression for diffusivity in the presence of a harmonic trap. There we have seen that the structure was this, that effective diffusivity was Peclet square divided by this quantity, so there should be a closing bracket here. This quantity and the effective timescale inverse. So this timescale inverse involved there the trap stiffness and the inertia. So here what happens is that, but if you think, so this is the timescale of the collision time. So if you think about two particles which are colliding with a harmonic potential, and if you increase inertia, what happens is that they spend more and more time at collision because they can penetrate each other, stay for a long time inside, and then they will come out of that collision. On the other hand, these simulations are done using hardcore-like interaction. So where if these two particles come and collide, they will bounce back. So the behavior is completely opposite with respect to the harmonic interaction. In harmonic interaction, you spend more time as you increase inertia. But in this case, for a finite inertia, if you keep on increasing inertia, this will bounce back faster and faster. And that's what happens. This time inverse then becomes proportional to m. And if you plug that in, then you will see that, and of course it will also depend on the activity Peclet, and that dependence is equivalent to any kind of interaction. So if you plug these two things in, you see that at large enough m, so this Peclet square behavior, there is in the denominator there will be m times Peclet. At large enough m, this can also become Peclet. And for any intermediate m, the exponent can be in between Peclet square and Peclet. So, and if you look at this departure from the equilibrium fluctuation dissipation relation, again you see that this decreases as you increase inertia. So with this I stop and will not get into the other part.
Earlier part when you showed the free particles, you showed the excess kurtosis.
Yes.
The dependence on the dimension, I didn't understand. Can you explain why it seems to depend on the dimension? Yeah, this one.
Yeah. So, and first is that if you even look at from the Gaussian process, what is the value of the kurtosis for a Gaussian process? That guy, of course, that itself depends on dimension, right? And then what you calculate here is that this is the ratio of v to the power 4, this steady state quantity, and then ratio of that. And if I assume that my process was a Gaussian process, which it is not, and take my v square from this process. And if I assume it's a Gaussian process, this will be the quantity that one will predict for the fourth moment. And then this guy is the ratio of these two. So as a result, it occurs.
So the question is the swim pressure that you said. And
Yeah.
you said the swim pressure goes to 0 as the mass.
Goes
m-
as 1 by m.
Yeah, so basically at large m it goes to.
Yeah.
Is there an understanding why? I mean, I thought the massive thing should have more swim pressure.
So my feeling is that you are pumping in certain energy, and this velocity, I mean, to maintain that velocity, if you have larger and larger values of m, so swim pressure goes as like u dot v average, right? So orientation f0 u dot v average. That's what swim pressure is. So that v quantity, you can imagine that for a given amount of, let's say if I just think about a driven particle, I give a same drive, but my mass is much, much larger, so then my steady state v will be much, much smaller. So somewhat like that one can imagine.
So you seem to have calculated diffusivity for on both sides of the critical Peclet, right?
What critical Peclet? Critical means?
The critical point.
You mean these phase diagrams?
Doesn't have any critical point.
There is no critical. I mean, although I'm saying is phase transition, you know that this is like single particles properties, and these are actually crossovers. I mean, so every time saying crossover is so just replaced by yeah.
I have a question. What happens instead of the active Brownian motion if you just take the active Ornstein-Uhlenbeck process? Okay.
Yeah.
So then you can calculate everything, right? So
Yes,
what
yes,
is the
yes.
inertial effect there?
Yeah. So only difference is that of course kurtosis will be 0 always, right? By definition, and active Brownian particle. Yeah. So whatever results I have shown there for this steady state second moment level results, they are exactly the same.
Exactly.
They're exactly the same. You can just map it.
And you will still see that the effect of inertia is still
Yeah.
I'm not sure I got the explanation why you see the double peak. So I mean, do you have
Double
a-
peak of the probability
velocity.
distribution, right?
Yeah.
Okay, so
So really, if
so
you should explain it to your
basically, idea is that you have this active velocity, let's say, and this. We should interpret it as an active force. I have a v dot equation. I have an active force, and this active force has a certain value, and there is an orientation of this. But that orientation has a persistence. But if you look at it for a very, very long time, it will be going in all possible direction.
Okay.
That orientation. So the steady state, I mean, if I think about v dot equal to minus gamma v plus force, steady state will be given by that amplitude v equal to a force by gamma. So that amplitude is the non-zero value of going from v equal to 0. So that's the non-zero speed. But this non-zero speed, with that speed, I can go in any direction. So as a result, what I will generate is a distribution in a two-dimensional space that will generate a distribution which will look like a ring.
Okay.
And that ring, if you project onto a 1D thing, will
becomes-
look like a bimodal distribution.
Okay. So this is not a result. Okay, I will discuss later with you. Yeah.
Okay.
So for the, did you say that you get power law tails for the velocity distribution for this trapped case in some?
Yeah, right.
So do you understand it analytically?
No.
Like you get long power. Yeah,
Yes.
Okay.
So, so about the distributions, we don't have any understanding. I mean, apart from these limiting cases, I mean, bimodality you can easily show.
But in that
beyond
case also, you can in principle compute all moments, right?
all moments you can compute.
But you can't
Yeah,
show
yeah.
the power law from there.
Yeah.
You should, huh? Yeah, no, that it should
No.
show up somewhere, right?
No, but there's a heavy tail. Yeah, the heavy tail I don't know. Yeah.
If
Yeah.
you can calculate all the moments,
Beyond.
you should be able to derive the...
They should diverge, right? Yeah.
Yeah.
Then they should. And another thing is for Ornstein-Uhlenbeck, I guess it's always Gaussian, right? So you won't
Yes.
you won't get any like this double hump and all that.
No. But late time behavior's dependence on inertia, that remains up to the second moment.
But the noise is also Gaussian. He's saying the.
So you were showing some some definition of entropy production. So what kind of entropy production is this?
Entropy production is there is an activity, that's the entropy you produce to the environment.
Yeah, but normally when you write entropy production, you write path probability and all.
Yeah,
Does
yeah,
this satisfy
doing all those
locally?
things.
Does
When
this
you do all those things, then you get an expression.
Yeah.
That expression, then you can calculate exactly. So that expression turns out to be some second moment level of calculation. So that calculation then you perform, and then there you get finally this expression at the steady state entropy production rate.
Yeah, so but when you do that, you assume there's a local detail balance or something like that. But for this active systems, there is no local detail balance. Is it?
No, I don't
Am I
understand
missing?
why local detail balance. There is a path
Yeah.
probability distribution.
We'll run out of time. Okay. So we'll meet at 11:30 again, 20 minutes, right?
I'll just make a quick announcement. I think for those of you who has eduroms, the Wi-Fi should work. And people for whom edurom is not working, there is this RRI conference, and this password is here.